and as you can kind of see, they tend to lie at slightly higher luminosities, perhaps unsurprisingly, because they are the far away and the easiest things to see are the bright. And what the question is, when you try and infer the mass of these black holes from the luminosity, you can either do so through assuming an Eddington limited accretion rate, and then you can get some kind of mass estimate on that, or you can measure spectroscopic line widths. I think most of these in this panel, in this figure and figure 1, are from magnesium-2 line widths. But since JWST has come online, you can also start doing this with H-beta as well at high redshifts, which is potentially more accurate or slightly less of a scatter. Someone who knows more about observations can comment on that. But there is quite a scatter in these. There's quite an error in an uncertainty in these observations of the inferred masses. However, even taking into account quite a large error on this, you have inferred masses of 10 to the 9, or even up to 10 to the 10 solar masses. Yeah, there's a few more handouts left if you need them.
Sorry.
Who wants? There's one left.
Yeah, I'll take one. I'll make up one there. We'll share.
You share?
We'll share.
So the question then becomes, how did they grow so big so quickly in the early universe? And now, since JWST's come online, we've kind of pushed this problem a little bit further. It's not necessarily a problem, but we've found smaller black holes even further away than previously before. So this second figure here shows I believe, still the highest redshift black hole to date, as far as I'm aware, still at redshift 10.6 in a galaxy called GN 1011, which was this galaxy was detected by HST because it was very bright, even and could be detected, was in HST's bandpass. But then has been looked at by JWST, and this inferred black hole has been found. Now this has a mass of about 10 to the 6 solar masses with chunky error bars, etc. And so this is kind of pushing back further in cosmic time. So the black holes have had even less time to grow by this point. There's two big uncertainties in kind of the theoretical modeling of these black hole growths. Is where did they start? aka what initial black hole masses are there, what seed masses is the usual phrase we'll use, and how fast can they accrete. And I'll talk a bit more about both of those in a little while. But it's kind of worth saying that if you see these black dots in the top right of the second figure, the ones to the left, like the grouping of 3 on the left here, are all quasars with inferred masses of 1 billion solar masses, 10 to the 9 solar masses at greater than redshift 7.5, which you're pushing your problem back at 200 million years, even further into the past. So you've got to grow these things pretty early. Now, the first thing I was going to talk about and potentially open up discussion is about seed masses of these black holes. So there's generally a few thoughts about what, theoretically at least, where these black holes originate from. The one we understand most intuitively is things like stellar remnants. Because you have a massive star that dies, leaves a black hole behind. They're generally up to 100, maybe, according to this plot, at least up to 10 to the 3 solar masses. So these are quite small. And to grow a black hole seed of 10 to the 3 solar masses to be 10 to the 10 by redshift 6, which is the largest inferred mass that we have at high redshift, it has to accrete at the Eddington rate constantly from redshift 23 or something like that onwards. So not only do you need to have the seeds in place very early, you have to maintain a very high accretion rate for a long period of time. And that's potentially quite hard. We can The other option is you have a larger initial mass. And so you have a heavy, what's called heavy seeds. And these are usually inferred to be from things like direct collapse black holes. And that's what this bottom right figure here is talking about. So this is looking at gas density. And it goes to like very high values if you go towards the right, versus temperature. So this is a phase diagram of gas. And as it collapses, as gas cools and collapses, usually what you'd expect to happen at low redshift is that it would fragment and start to form stars. At high redshift, there's a couple of things that help you in this case to stop that from happening, so you kind of get a monolithic collapse all into one object. One is that the metallicity is very low, and so the cooling, you don't get cooling from metals to help you along the way. The cooling rate is therefore suppressed. And there's also this background radiation flux from other stars or kind of other things in the background. It's usually called Lyman-Werner radiation. And that, if you're illuminating gas that's condensing and collapsing enough with this radiation, you can prevent it from forming molecules and starting to cool molecularly. And so it just keeps collapsing to higher and higher and higher densities. And kind of theoretically, that can lead to direct collapse black holes of 10 to the 4, 10 to the 5, maybe 10 to the 6 solar masses. Which is kind of the limit of where we've been starting to push to in terms of observing kind of intermediate and supermassive black holes at least. The ones inside the Milky Way we would observe smaller than that.
So what is known about the time scale for this direct collapse? Can this also happen by redshift 20?
That is a good question. You need a halo to have formed to be able to collapse stuff into, right? You need a gravitational well to do so. If you can get that by redshift 20, then potentially you can start seeing these things early. You don't need to do, if you're starting with a larger seed, you don't necessarily need to have as massive, seed as early as you do for a stellar mass seed.
I guess that was my question. So let's say I can make 1,000 solar mass seed very early in the universe, but I have to wait some time for the 10 to the 6. Do you still wait, or?
This is the way, it's kind of, we don't know, there is a degeneracy here, right, between the, when the mass of this initial seed and when it is seeded. If you could have a 100 solar mass black hole seeded at redshift 30 that grows at Eddington and becomes, it suddenly you measure it at 10 to the 5 at redshift 12, 13, etc. And I don't know if anyone else was to jump in on here, I'm not sure.
Eddington is a decade of growth every 115 million years. So if you can go 10 to the 6th versus 10 to the 3, that's 300 million years of extra room you have to play with. So.
That's my question. Is that 300 million sufficient to have your direct collapse? I mean, in these scenarios, I mean, do they give a time scale?
I'm not sure off the top of my head actually. If they have a time scale for how long, when you expect direct collapse black holes to appear. Like in cosmological simulations, we don't resolve most of this, obviously. But what we tend to do is kind of skip the problem and say, once a halo has reached a certain size, we just plonk one in the middle. Yeah, we plonk one in the middle, exactly. And from that point, then, even with Eddington capped accretion, we can, in certain situations in large enough halos, reach the kind of quasar luminosities that we observe. Now, whether you want to call that a direct seed collapse black hole that forms at redshift 12, for example, or it is a kind of unresolved accretion onto the stellar mass seed that's starting earlier, that I don't know, and I'm not sure how we can start to.
Yeah, Ramesh, a few years ago there was a paper in UL, Ferrara, other people, I think 2015, 16. They were saying it's named the brief era of direct collapse black hole formations, and I don't remember exactly the numbers, but it should be possible to form direct collapse black holes between redshift 23 and redshift 16.
Oh, okay, that's very early.
Yeah, and just a few million years in which you can actually have magical conditions of comet dissipation.
Okay, thanks.
Okay, well that's potentially fairly early then. So for example, this highest redshift black hole discovered to date is about 10 to the 6 solar masses, so the very upper end of what you might guess is a direct collapse black hole by redshift 11 or just below redshift 11. And so either it has been formed recently and it is just that mass, or it has been growing from a small seed for a long time. You can see that in this blue region here.
Yeah, I just worked out the numbers in Cosmocalc. I think they respond to Ramesh's question. So the age of the universe at redshift 15 is 0.28 gigayears, at redshift 30 is 0.1 gigayears. So, it's 0.18 gigayears between redshift 15 and 30. So that's a lot of redshift, but not a lot of time.
Yeah. Right.
So I think you do good if you make heavy seeds, at a somewhat lower redshift, because you start from a much higher starting point, you gain in terms of growth.
I mean, a lot of the.
So I was looking at the paper. It's Melanie Habazut at Max Planck. I can show you the figure right there, but the number density of direct collapse, the payloads that can host at ACDH at a given redshift stretches out to redshift 20 in this particular simulation, with a number density of 10 to the -4 to -8 per co-moving megaparsec. So box of the co-moving megaparsec. At redshift 1.
So how does it compare with the number of observed most massive black holes? Numbers of out, or before the scale was produced, seeds by the red colors. Can you explain?
I'm not sure what the quasar density is off the top of my head.
It's about 1 per gigaparsec cube at redshift 6, so someone does the math. Luminous. The most luminous are about 1 per gigaparsec cube at redshift 6.
But C or P megaparsec?
C.
It is worth saying as well, and what we'll talk about in a little bit in the future, is that this is luminous ones that we can see. And there are potentially, for various observational reasons we can start talking about in a little bit, there's reason to believe that a lot of black hole growth is obscured in the early universe, because partly because everything's just denser and everything's collapsing and it's a mess. Partly it's just to grow to these large masses, you need to have a lot of gas inflow onto the centers of these galaxies. And so there's a lot of gas there that could be blocking the light escaping. We'll talk about that in a moment. So yeah, what you kind of end up with in this direct collapse scenario is that basically if you can keep gas at roughly 10 to the 4 Kelvin as it collapses, then it won't fragment and form into stars and will just kind of go all the way, just form one black hole directly. And so you need this kind of background radiation, as we've talked about. You need these kind of very specific conditions that only exist for a brief time in the early universe. So it's potentially a solution, and as we keep finding smaller black holes at high redshift, then that will kind of give us a bit more information on this. The other question, which is hard to look at, is how fast that they can accrete. So this is how much gas they can get into the black holes and grow over time. And kind of traditionally we think of that as being capped at the Eddington limit. So I don't know if anyone who doesn't know what the Eddington limit is. But yeah, you have lots of radiation coming out and material falling in, and the radiation pressure balances the pressure of the gas coming in. And you can prevent accretion higher than that rate, in theory. But there are plenty of theorists who think that super Eddington accretion might be very necessary to grow these kind of black hole masses. Or can such a high accretion rate be sustained? And also, would there be observational signatures of that? And so kind of briefly, the random slide from a talk that I didn't give because I had COVID. But if you have super Eddington accretion, right, you've got an accretion flow pumping out radiation, and you've got gas moving in. If that gas is moving in, if you've got enough gas being dumped onto this black hole, if it's optically thick, the photons will scatter as they're passing through the inflowing gas. And so they'll be moving out with a diffusion speed rather than the speed of light. And so if this inflow, if the inflow gas is faster than this diffusion speed, you advect the photons inwards, they don't escape. And so this happens within what's called the photon trapping radius, which is dependent on the accretion rate and the Eddington rate and the radiative efficiency and various things like that, and the Schwarzschild radius. Well then, if you, oh yeah, I made a funky animation to show what scattering looks like. And I can't skip it.
You guys, the cloud has to be moving in.
Yes, that's true, yeah. I would have finished it, but then I COVID, so I didn't. So, but actually, if you look at the maximum luminosity that you actually can, so this is from like Bergelman 70, I can't remember what year it was. Well, this was kind of assuming spherically symmetric accretion onto a black hole or a compact object, and radiation can have spherically too. But if you kind of then estimate the actual luminosity that is escaping from out from this object, it ends up at Eddington. Even if you've got whatever, it becomes independent of the accretion rate. Because you're only getting photons escaping from outside of this photon trapping radius, then whatever you do, whatever you look at, you'll end up looking with observations with brightness at Eddington. And that kind of leads into the problem of, can we ever observe super Eddington accretion more than like a factor of 2 or something? You can see in this top panel in the first figure that showed that these diagonal lines here are showing kind of Eddington rate at a given time. And like most of the low redshift quasars sit below Eddington with kind of some fraction at like 2 times Eddington, 3 times Eddington, something like that. But detecting hyper Eddington accretion would be hard.
I think it's a great point. This is actually a great paper. It's a 1979 paper. But today, we have tons of direct simulations where you can get whatever super Eddington you want, provided you have the gas. You have to supply the gas, but if you give the gas, the black hole can eat at any rate. And you can compute actually what's the luminosity, what's the power coming out, etc. And the biggest kicker is if there is a jet. Because if there's a jet, it can carry a huge amount of mechanical power. So the only thing you worry about is radiation. Yeah, you can get a few Eddington.
There's a few slides on and talk about that, but it's kind of not what I'm to here. But yes, it's a very good point, is that this was all assuming nice spherical symmetry, which obviously accretion is not. And you have feedback from these black holes as well, mechanical, not just radiative feedback. And so if you're blowing out gas with the jet, for example, then potentially you could get things brighter than anything observed. We have, as far as I'm aware, we've not detected anything like crazy high Eddington.
Oh yeah.
Is it just in like supermassive black holes, or in kind of Milky Way sorts?
Smaller scale, but yeah, I have at least a couple of objects in mind. One is a neutron star in a binary, and it goes like 2 orders of magnitude above the Eddington limit. So it's definitely something which is observed, and simulations do. So I guess super Eddington can occur, but the point is that, for example, in this plot, it seems like at a certain point you have to quench it. And it seems like sort of fine-tuned the point in which you quench it.
Yeah, so this is the kind of the point of this plot. Yes, if you, this black hole at redshift 10.6 was inferred to be accreting at about 3 times Eddington, something along those lines, with a fairly large uncertainty because of the uncertainty of black hole mass. if that was maintained, you can see this red trajectory of where it's coming from, where it's going to. You can pick whatever seed you like and you just grow it really quickly and it's fine. Obviously, if that was maintained, then you get a ridiculously large black hole that we don't observe at low redshift. Sustaining Eddington accretion is potentially hard because of the feedback that we just talked about, and I'll come back to that in a moment. Yes?
Yeah, coming back to the super Eddington configurations. So I think this argument is valid when you average over the solid angle, like over 4 pi, and when we observe, right, we observe in a particular direction, and if the release is not, isotropic, then you can, I suppose, get those, neutron stars. You don't observe at average over 4 pi.
That's a good point.
Right?
Yeah.
So I wonder, in this model, for example, do we generically expect that when it's super Eddington and the energy releases along the jet or some axis or something?
So, yeah, we would, in these kind of scenarios, and a lot of like GRMHD simulations have done these kind of things. I think we've got a few slides on it, but we don't need to look at it. But yeah, you can end up with, in theory, much higher luminosities coming out of these things.
It may come in a different bag.
Yeah. But
It's not just the redshift, even the physics looks different.
But if you're accreting a super Eddington and you're dumping this huge amount of energy into the surrounding black hole, maintaining the constant large accretion rates onto the center of the galaxy, which you need to maintain the super Eddington accretion, is very hard. So you probably end up with more of this. Sustaining it for a long period of time would be very difficult, I would suspect.
So actually, on this same point, if you are making a seed, let's say 10 to the 5 or 10 to the 6, that guy is of course accreting that highly super Eddington, right? It's a big fluffy thing, and it became a black hole, and you can say it went through, vastly super Eddington accretion. All these questions really you should ask even at that level. How do you make that seed? Because it has to be formed at a very, very super Eddington rate. I guess nobody worries about that at the moment.
Yeah.
Because it hasn't been really simulated.
That's a good point, yeah. I mean, in cosmological simulations, we can't do any of this. So what we have started trying to do is what we can try and do is inject like appropriate amount of feedback energy that we expect to come out of these things and see what that impact is on the galaxy and the surroundings. And that's what I did recently, and I'll talk about that in a little bit, for actually modeling at the galaxy scale right down to the accretion rate, accretion disk. Very high. Okay. So, yeah, these are the problems that we're ending up with, right? Is that we don't know where we're starting from or how fast we're going. So getting along this trajectory is tricky. So from this redshift 10.6 thing, if you assume that this accretes at Eddington, then you can explain most of these high redshift quasars. As I said, sustained Eddington accretion, because of feedback, let alone super Eddington accretion, might be quite tricky to actually do in practice. Because of feedback primarily. So, we're going to spend most of the time, I think, or half an hour left, talking about prospects of what we can do to try and look at this in the future. And also kind of about the hosts of these things, and what that can tell us about the growth of these early black holes. I guess we could start with this top right figure, which will be the easiest one that will tell us lots. This is a sensitivity curve, expected sensitivity curve from LISA, the gravitational wave, space-based gravitational wave observatory that's expected to launch next decade. And this kind of high, these heavy seeds between 10 to the 4 and 10 to the 6 are kind of nice, sweetly in the middle of the sensitivity curve of LISA. And if you look at this, the y-axis, this is showing this, the numbers and the colors here show the signal to noise that you would expect from just between them. And if you could look at kind of 10 to the 5, for example, this kind of fiducial heavy mass seed that you would have, with LISA we were able to detect merges between these with a signature noise of 200 out to redshift 20. So this, in theory, will be able to tell us quite a lot about the early growth of these black holes, because the actual mergers between them, or at least how many seeds we expect to get. Because if you form these direct collapse black holes, and there's not many of them, then you won't expect that many mergers of them, these kind of redshifts. So it will start to really kind of pin down the frequency of the heavy seeding if that does occur. And it's not kind of sensitive down to like the stellar masses, stellar mass black holes that LIGO would be, but it's not sensitive enough for this distance yet. So I think that will probably be one of the biggest game changers that will tell us a lot about kind of early black holes potentially, hopefully. I'm sure there's lots of technical problems in how to actually do this, and I'm sure gravitational wave people will be scratching their heads for a while. But in this plot, at least, it all looks great.
The main point is that this plot, I don't think, accounts for this plot is very old. I've been seeing these plots at conferences for 8 years, something like that, and there's a lot of stuff going on from then on, and the point is that we found sources of noise, like astrophysical sources that can emit noise, and it's going to be very difficult. Again, nominally the sensitivity goes so deep. So anything that exists and emits in this band, you're going to have to take into account.
Yeah.
So that's the biggest issue. It's not going to be the instrumental noise, provided that it applies with the specific that it has today and it doesn't get this scope like other ESA founded missions. But again, the point is going to be the astrophysical noise.
Yeah.
In this kind of scenario.
Yeah, I think that's a very good point.
I'm not even mentioning the stochastic background.
A very good point that it will be hard to do, and this is optimistic, would you say, assessment? Which is why it is useful to look at what else we can use as well. So these top left and middle left panels, okay, so these are kind of interesting and slightly contradictory plots, but not necessarily. So this top one here, we'll start with that one, is looking at the probability of a satellite of a high redshift quasar being at a given velocity, or below a given velocity, a line of sight velocity this is. And the kind of solid black line here, the black and orange lines here are from simulations. And so these are halo simulated lambda CDM universe that's collapsing. And these black lines are looking at satellites around slightly lower mass halos. So these are like 5 times 10 to the 11 up to 1 times 10 to the 12 solar masses by redshift 6-ish. Something along those lines. And the orange here is a more high mass sample, which goes more like 5 times 10 to the 12 up to like 7 or 8 times 10 to the 12 solar masses by redshift 6. So it's not like this a factor of a few difference here. And the dot dashed line here is the observed, look at this from JWST and ALMA and various systems that I can't remember exactly what the observations come from in this. And what this plot points to is that the high redshift quasars that we observe, the bright ones that we observe, which is specified, are most likely hosted in the largest likely objects in lambda CDM universe. They're in these enormous halos that are 5 times Milky Way mass at redshift 6. The middle left plot, I don't know if you wanted to say a few words about this.
Yeah, sure. I think so. So I don't think actually the cost of had JWST observations in it yet, and that's exactly what the bottom plot next shows. So the top one I think was ALMA and Muse or something, and so we know from simulations, right, and from observations to some extent, although it's really difficult, right, at high redshift to do this, that those luminous quasars should be hosted in the most massive dark matter halos that we have available at those times. And you can, so up to redshift 4, this has been done with clustering studies, for instance. So you measure the autocorrelation between quasars, that gives you a scale length, and then that CDM lets you relate this to the host dark matter halos of those. And so in this middle panel here on the left, middle plot, the blue curves basically tell you what previously done many, many times. People have done this with SPSS and all kinds of surveys. And basically what I show you is we know roughly what distribution of dark matter halos we have in the universe at redshift 4. This is the dotted line there. So we know what sort of halos are in the universe. And then due to this clustering, you can figure out what part of those halos are occupied by luminous quasars. And that's the blue solid curve with uncertainties there. And what you can see nicely at redshift 4 is exactly what everyone was predicting from simulations and shown many times before, that quasars sit in the most massive dark matter halos that we have. Now, people have tried to push this to redshift 6 and beyond many times and with various levels of success, I'd say. But JWST has really been game-changing in that aspect, because now we can actually, we still can't measure the quasar autocorrelation function simply because we don't have enough quasars at redshift 6. This is the 1 per gigaparsec cube that I mentioned earlier, so the number density is too low to do this. But what you can do now, and that's where JWST comes in, is measure the cross-correlation between the quasar and surrounding galaxies, and if you know the autocorrelation between galaxies, you can infer the autocorrelation of quasars. It's a bit convoluted, but mathematically it works out. And so that was something that the first, and all of this is very preliminary, right? The data comes for like 6 months or something, but that was something that people have been working on over the last, including myself, over the last 6 months or so, trying to get the clustering of those high redshift quasars. And this plot keeps on changing, but it's now getting to a certain level of consistency. This is by a student at Leiden, Elia Pizzati, who did exactly the same analysis at redshift 6.5. So he took a clustering measurement from JWST and tried to infer where those dark matter halos, where those quasars are, what type of dark matter halos the quasar at redshift 6 lie in. And to everyone's surprise, they seem to be lying actually not in the most massive dark matter halos that we have at redshift 6, but in slightly lower ones. And that has been, none of this is published, so take it with a grain of salt, but it's 2 independent groups and 2 independent methods that have been confirming these results. And what that means is, well, 2 of things, what it could be meaning is that the UV luminous duty cycle, so the time that these quasars, these galaxies spend as luminous quasars, is actually much lower than the age of the universe, which could imply that we have super Eddington accretion. So it could be another evidence for we have to grow them. Not only do we have to grow these black holes within like the billion years that we have up to redshift 6, but actually the duty cycle is only 1% or so of that. It's actually 100,000 or 10,000, 10 million years. Or it could imply that there's a lot of obscuration, which I think is probably at least partial. Well, probably is both to some extent. But it could imply that we have a lot of obscured quasars. Basically, everything that we don't see, all those massive halos where we don't see a quasar, and then still hosting a supermassive black hole. And the 2 options is either it's off, it's not accreting at the moment, it's not a quasar, or it's obscured.
Why? Are there any feasible explanations on why larger halos should have some mechanism, either obscuring or quenching quasars? Because this seems to be implied by this result, right?
I think no one knows, I think is the short answer, right? I think this is the first time we're doing this measurement at redshift 6, and it's contradicting every simulation. And so it could also obviously be just systematics in the measurements. JWST, who knows what's going on. But so far it seems to be interesting. But why the most massive dark matter halos might not be necessarily hosting a luminous quasar? Your guess is as good as mine. I think there could be a lot more obscuration happening, especially at those very early stages, which is another thing we see with JWST, where much lower redshift, 5 or so. All those little red dots is like obscured, which is in the plot below. Obscured AGM.
I think it's worth noting in simulations that it is incredibly hard in simulations to grow a quasar or a 10 to the 9 or even larger black hole in a simulation that isn't in a very large halo of high redshift. This is a very difficult thing to do, primarily because of the amount of material that you're dumping onto the galaxy. If you have a larger halo mass, it has more stuff around it and it's accreting at a higher rate. And that also then has the impact is that you've got more material that could potentially be blocking the observations of these in the UV, which is where potentially things like X-ray will come in. Probably, I think we probably need more like some future telescopes on currently exists too often for. Yes.
Yeah, so there used to be this old argument, the so-called Soltan argument, which said you can't have too many obscured quasars because the amount of quasar light that we do observe and the amount of black hole mass we have in the universe kind of match. So the more you obscure the quasars, the more you have to say that the ones that you do observe are, you know, absurdly super Eddington or some such thing. You know, that was the basic calculation. And everything used to work. I'm talking about 20 years ago. And I think Soltan still works. The question is, how can you say 1% only shines visibly and 99% are obscured and still satisfy Soltan?
Yeah, it's a good point. I think Soltan works at redshift 2 to 0, right? The argument is that.
Right. So you have to say that, okay, I hide them like crazy at redshift 6, but then at redshift 2, they're all visible and somehow I can match everything.
Yeah, that's not a crazy idea though, right? That the obscuration changes. I mean, at redshift 2, we know from X-ray surveys, obscuration is 50% or something, maybe not even. But there's definitely evidence that it increases with higher redshift. Now, whether it increases to 99%.
But has anyone folded that back into the Soltan argument and shown that it all works?
I don't think so.
I think it's definitely a worthwhile exercise, right? Come up with some history of obscuration versus redshift and growth, black hole growth, whatever, and see how much it can shift the original argument. Yeah.
Is kind of like the parameter then like a hidden fraction of growth or something like that?
Yeah, I think the way
is
it works is
70% hidden, 95% hidden or something?
Yeah, I think I mean, my instinctive feeling is the way it would work is the following. You can have it all 100% hidden, so long as it's early in the life of a black hole. You know, you can do all the E-folds you want, but then, you know, keep the last couple of E-folds open so that you will see the light, and then Soltan will be happy, but you could have obscured everybody as much as you want. But I think this has to be quantified to see whether something like that.
That's kind of the idea of in cosmological simulations. Is what we need is that when the black holes get massive enough, they kick out crap in feedback, and so you can suddenly see them again.
Right.
And so it's kind of one thing. While a lot of that kind of kicking out is tuned to reproduce things like the stellar mass function and the redshift, the kind of impact on the obscured fraction, I'm not sure. Someone must have looked at this, but I can't remember. Don't know if they have in cosmological simulations.
Yeah, okay, I think this crowd should be able to do this. Give them the latest updated view on Soltan and obscuration.
Yeah, so whilst we're talking about the impact on the galaxy of these things growing, the kind of these, I'll shamelessly plug the bottom right plots from my recent paper. where this was looking at 3 different scenarios. One which was a without any black holes at all. One where it was a fiducial model that was calibrated at redshift 0, so it's kind of a standard simulation model, we use that term loosely. And one where I seeded the black holes a bit earlier and allowed them to accrete it up to twice the Eddington rate with a Bondi formalism, don't shout it. Also kind of lowered the quasar efficiency, so the amount of energy being input as feedback into this per like a unit mass accreted. And so what that does is helps you grow the black hole earlier. So this on the right, there are 3 runs here. This reference run is the one where I've grown a 10 to the 10 solar mass black hole by redshift 6. So this is kind of matching mass-wise roughly the largest black holes in the early universe. And there's a couple of interesting things about the impact on the galaxy and the CGM around it. So this kind of top left of this bottom right panel is looking at the metallicity of the stellar metallicity as a function of time. And if you have early black hole feedback from a massive black hole that's grown even earlier in the universe, then you can, partly because you produce less stars in the first place, and so you have less metals in this, or also you eject quite a lot. So you end up with a lower galaxy metallicity by redshift 6 than you would in a run without AGN or with a fiducial run. So this Fable run is the fiducial calibrated to redshift 0 result. And you can see in the stellar metallicities here, there's very little difference between a run without AGN at all and the Fable run, which has a 10 to the 9 solar mass black hole by redshift 6. And it just doesn't do much to these metallicities. It's kind of a timing thing of when you inject this feedback. It's quite important. Well, then it also does have an impact on the right here is the stellar density profile. And so without black holes at all, you have very peaked very high densities of stars in the center. If you have some feedback, then you can start to flatten this a little bit more. If you have very early and strong feedback, you can kind of redistribute the stars in this, or potentially where they form as well, and you end up with this much flatter profile of stellar densities. Now these are things that will be very hard to look at in high redshift galaxies, potentially because of the quasar being so bright in the middle. These are some predictions from recent simulations, but this bottom panel here is, I think, could be quite interesting. It's links predictions for what the gas around the quasar would be, how it would look. And so this is, if you're assuming perfect removal of the quasar at this point. But if you can kind of see the inner like dot dash line here is the expected PSF from an instrument like LINX. So there is quite a lot of emission coming from outside the PSF of the instrument. And when you have kind of this early growth of black holes, much earlier growth and kind of this energetic early feedback, you really reduce the X-ray brightness of this kind of thing. If you kind of make profiles between, you can sort of start to tell between the no AGM one and the one with the fiducial one. So you could start to see how the impact of feedback from these things could, you could decide to estimate how much gas is being injected by these things over its history, which is then quite related to the growth history of these quasars. But then the other kind of flip side of this, I don't know, Fabio, do you want to introduce your plot by this bottom?
If you want.
I don't mind. So what this is showing, I hope I don't get this wrong. So in blue here is the like low redshift relation that we expect between black hole mass and stellar mass, or stellar mass and black hole mass. So this is fairly nice correlation at low redshift, right? It's relatively tiny. And all of these points here are observations at a variety of redshifts, but generally about redshift 4 up to about, is it 7?
7, yeah.
Which all lie well above this redshift zero relation. Now, there are kind of, you can kind of see with some of the error bar, there are kind of considerable uncertainties on these things, but they're pretty far outside of what you'd expect from the low redshift relation. And so, I'm not sure exactly, was this a fix you did to the, to
No,
make
so
an
this is, so the red part is the result of MC algorithm. They take into account many things, including the flux limit, etc. So it's slightly more accurate than the statistics.
Yeah.
It's not that big report.
Yeah. Okay. Well, yeah, this is basically implying that black holes are a lot more overmassive at high redshift compared to their host galaxy stellar mass than they are at low redshift. Now this, I guess, could partly start telling you about seeds, because if you find galaxies, regardless of stellar mass, you end up with the same black hole masses in all of them. You kind of might start implying that the black hole mass there is some kind of flaw on those things. And I guess the points here do look relatively flat, relatively flat, I suppose, but that is.
So you're talking about the data points?
Yeah, but I guess that's
So,
got problems with.
okay, there's a pretty funny story about this. You know, when we started to do this, we took the local relation as a prior to infer the high redshift relation, okay? And we found like a high redshift relation that scales up the black hole masses by a factor of 10 to 100 approximately, but the slope is pretty similar to the low redshift relation, okay? So we thought, well, maybe this is just like a bias. We're just saying, okay, it should look like the low redshift relation, and you know, we're probably making something wrong. Because you know, if you look at the points, it looks like flat than the local relation, okay? So we remove the prior. So we say, okay, this doesn't have to look like the local relation, and we got the same slope, slightly different by a factor 1 or 2%. Okay, so we started to ask ourselves why the points look like flatter than what we are actually finding out. Okay, and there is two reasons for this. One is that I would like to draw this. Okay, so imagine that the data points are like this. Okay, instead the high redshift relation that we are finding are like this. Okay. There's one effect here at the low mass end. The problem is that some of those points, some of the data points are quite close to the JWST limit. Okay? So what the MC algorithm is saying, okay, the data points here are here, but it's possible that we are missing some of the objects here. Okay? It's possible that we are missing some of the black holes that are below the JWST limit. Okay? So instead of having a relation that, so it's basically increasing the slope here, okay? Because it's saying, okay, it's possible that we are missing something here. Okay? Yeah. On the other side, the problem is that the MC algorithm also takes into account the abundance of galaxies. Okay? So on the horizontal axis, you have on the right galaxies that are much more massive, so less abundant. Okay, so the algorithm rescales it. So there is a bias towards like lower mass galaxies. Okay, so instead of having a fit that passes through the data points, on this thing is increasing because it's going down because it's saying we're missing some of the data here. Yeah. While it's assigning more weights to galaxies that are at lower masses, and you're finding almost exactly the slope of the low redshift MM star relation without it being a prior.
Interesting. Okay. So yeah, that seems that the slope does seem very simple, but you end up with much more overmassive black holes compared to the stellar mass of the galaxy.
Is this the total stellar mass of the whole galaxy? Or?
Is it what?
star mass is a total star mass of the whole galaxy? Or?
It's a CSCD fitting, so it's basically whatever they can measure of the stellar masses.
Yeah, because I don't mean it's a snake question, but I thought that locally there's a stronger correlation between the velocity dispersion of the bulge and the total mass. So I was wondering if it can be explained by early galaxies being like more dispersion dominated.
If you look at Mariolino's paper, no, it's not here. What they are saying, they have a sample of about 10 galaxies in jades, and they are showing that the MM star relation is basically completely messed up, meaning that they are all over massive here, like this plot. But the M sigma and the MM dynamical relation are still kind of valid, also high redshift. So it's only the MM star relation that seems to be completely messed up.
Okay. So it's consistent.
Yeah.
Well, no, could that be to do with how you, the stellar mass measurements? I don't know. I'm asking.
I really don't think it's. I mean, it's possible it could be some systematics, yes. But you would need to be assigning to the stellar mass much more than you can actually explain that is. I mean, there is a factor of 100 in some cases. It was a paper by Uncovered, I think, in which there is one of the objects that is like almost the same mass of the black hole and stars. So
the only thing I worry about this plot is, whether we just see the absolute tip of the iceberg and whether the scatter isn't. I know your paper argues against this, but whether we're not missing all the ones that are below the relation, basically.
So if you remove the JWST limit, so the JWST limit that you see there, it's calculated for a JWST near spec detection of the PLR region H alpha at more than T sigma. Okay? If you remove the JWST limit, saying JWST can observe any black hole, okay, it doesn't really matter on even a 10 solar masses black hole redshift 7 or 8. This thing shifts by 0.3, okay, which is less than the scatter. The scatter is 0.69. So, I mean, it's possible that some of this is systematics and it won't be like a factor 10 to 100 necessarily, but I'm pretty convinced that it's not all systematics.
Is there a reason why you're looking at the limit of H alpha rather than H beta?
Oh, because so we use the galaxies between redshift 4 and 7.
Okay.
You can only use between 4 and 7. H alpha arrives at redshift 7, then you have to use magnesium.
What happens if you try to bridge the gap between the two? Populations. Like local usually is very, very local. What happens if you take objects between, let's say, redshift 1.5 and 3?
So you're saying what's the redshift evolution on the ratio between the black hole mass and the stellar mass? I mean, there are papers 20 years ago suggesting that the ratio between black hole mass and stellar mass should evolve with redshifts. It's about 1 plus z at some power. It's a paper, I remember one of the papers was a paper by Avi and another postdoc here.
But I mean, with the SDSS, it should be possible to do it, to check.
It's really hard to measure the stellar mass of the host given that you have a quasar there. And so actually, it's been, so people have done with HSD up to redshift 2, and then above that, it's been just impossible until now JWST. So all those data points are JWST from this year. And so no one has done it no one has been able to see the stellar light of a host galaxy between redshift 2 and now. Well, with now, I mean between redshift 2 and what we can do now at JWST.
So
but I don't know actually what people have. It's a good point. What happens at redshift 1 or so.
Yeah, my point is what they mean by local. Like local is redshift 0 or redshift up to, I don't know.
0 to 0.1.
Yeah, this is basically
something you
0,
can
0,
measure in like
So-
parsecs.
Something between like
Yeah, it's a good point. I don't know. I'm sure people have looked at it, but I don't know what other books are.
As far as I'm aware, apart from all these bunch of objects, the lower overmassive black hole that was found, it's a redshift 1.9. There was like magnets 1 year ago or something like that, and like a bunch of them. Then between redshift 1 to approximately, there is basically nothing, because JWST was observing quasars of 10 to the 47, 48 per second were completely overshining everything, so you couldn't measure the stellar mass. That's why these black holes are 10 to the 46, 47 per second, so it's much different.
Well, I think we're about running out of time. So yeah. What? Yeah. So I guess thank you everyone for coming and participating. And yeah.
Thank you.
Thank you.